Hello again and welcome back to my computer vision channel. Today we will talk about RTDETR v2, so the second version of the model, called by the creators themselves the bag of freebies. So if we look at the actual paper, we can see that it is really short, just 4 pages, so it's going to be quite a short description. Basically all the algorithm basics are still the same as in RTDETR, but they did some tweaks here and there to improve the quality a little bit. So today we will be talking about that. And here's the plan for today. So the first modification, actually the first 2 modifications that they did, they all happen in the deformable attention in the decoder. So the first one is the variable sampling points count and the discrete sampling. So we'll go over what deformable attention is and what were the modifications. And then we'll jump straight to the code and then read the same stuff in the code for deformable attention, and also to look at other modifications that they did, such as dynamic data augmentation and the scale adaptive hyperparameter customization. So this is the actual scheme of how RTDETR v2 works. So it's the same as v1 basically, and it looks quite similar to DETR, the first transformer-based object detection model. So we start with just the raw picture. We pass that through the backbone, like ResNet50, then we pass that through the encoder, and this efficient hybrid encoder is the main introduction in RTDETR v1 that separates the interaction, fusion, and all of that. So if you want, I have a whole video about that on my channel. And in v2 RTDETR, the encoder stays exactly the same. And then we have the decoder. And in decoder, we have deformable attention for attention between queries and encoder memory. And this is the main modification in v2 version. So let's start with the actual deformable attention, what it is and what is the difference to normal attention. So first, the scheme of the actual normal attention, aka full pairwise attention. So as an input, an attention layer like that takes in 3 sequences. So each sequence, basically each element in a sequence is an embedding itself. And so they're called query, key, and value. So we first take query and key and compute dot product between every pair of embeddings to get the actual attention weights, W. And then we multiply value and the attention weights to get the output. And this is the result of the layer. So in the example of the vanilla DETR model, if we look at the decoder, so the queries are over here, that's why they are called queries, and then the key and value in the decoder comes from encoder output. So basically what we do is we take this query, multiply it with the key to get the attention weights, then we multiply value by these attention weights, and from there we get basically the new version of queries that is passed into the next layer as input. And so we can apply the thing layer by layer. So once again, in DETR decoder, cross attention, Q comes from these queries, called experts sometimes, and then key and value come from encoder memory. So here's an example of how that actually will look like. So let's say we are computing an output attention mask for one of such queries, right? And as we can see from the actual attention weight visualization, this query seems to be detecting a bird. It's quite good at that. The attention weights actually seem to show a silhouette of a bird. Despite that, to actually compute these weights, we had to look at every other pixel in the image. And looking at every other pixel in the image is actually a complex operation of taking this query, multiplying its embedding to the embedding of this pixel, and getting the one number for attention weight. So we can see here that most of these attention weights are actually dark, meaning that we don't want to pay attention there. Nevertheless, we keep diligently computing these attention weights every time, and this is like the most time is in the model is actually spent here in any transformer model, right? So most of these, despite being dark, we still take a lot of compute to actually calculate them. So in deformable attention, in deformable data, for example, the scheme is slightly different. So now, instead of trying to pay attention to everything and then seeing which places we actually don't want to pay attention to, we start in reverse. We start with a fixed set of points where we want to pay attention to, like these red guys here, and only compute attention with them. So the actual scheme now is a bit different. So we only use query and value, so we don't need keys here. We project query into what is called sampling offsets and attention weights. So now the attention weights don't actually use the dot product between two elements of the sequence. They're just projected from the query. So that's one big difference. And we basically use the sampling offsets to create the actual attention points where we want to pay attention to. To do that, we actually need an extra set of coordinates called reference points. So this is like the center of attention for deformable attention. And then the output again is computed as a weighted sum of values with these limited sampling points and attention weights. So in deformable data, again, we take queries as Q, we take encoder output memory as value. We decide on the reference points, either just projecting down the actual queries or taking the special bounding boxes that we have passed into the layer. So that's a whole new mechanism that's described in deformable data. We get the attention weights, attention offsets, all of that from the actual query embedding. And the result of that is now that instead of computing all attention weights for all the pixels that we might not even be interested in, we just take a limited set of points and just pay attention where we need to. Another important detail about deformable attention is how we actually get this output, having the sampling point and the weight. So it just so happens then that when we predict the actual offset, we usually predict a floating point number, so it might not actually land precisely on a pixel. And so then we need to decide what will we use as an output. And so classical deformable data uses what's called Bilinear interpolation, which looks at 4 neighbors, 4 grid points, and then computes the value of this pixel as weighted sum of all 4 of these. So it's a complex operation. In the original deformable data, it actually required a custom CUDA kernel to compute that. Now it's part of PyTorch. Nevertheless, it's a complex operation, and it's needed primarily to be able to pass gradient through this operation. So passing gradient through this means that we can actually train this sampling prediction head of the model, and it will move these attention points somewhere where it is most beneficial to the model. Another way to do the same is discrete sampling, where instead of taking basically 4 neighbors' weights, we just say that let's compute one nearest point like this one, basically converting our floating point number to integer, and then just sample that using normal tensor indexing. So this is much cheaper. It doesn't require any custom CUDA kernels, so it's easier to use in embedding application, for example, and it's faster, but it doesn't allow you to pass gradient through this operation. And so the way it will be used in RTDETR v2 is that we start training with bilinear interpolation, thus allowing the model to train these sampling heads to choose where to pay attention to. And then we switch to discrete sampling and train for a few more epochs just to make the other parts of the model used to that. And then during inference, we only use discrete sampling so that it's cheaper and it's more useful for other applications. So to sum up, in deformable attention in RTDETR v2, we have 2 modifications. So first modification is that the actual sampling point count, so the number of points we pay attention to, instead of being fixed per model, it's now dependent on the actual model size and on level. But as we'll see from the code, there's no actual dependency on the level. It's just that the actual sampling point count is different for different models. And second is, as we've discussed, we start training with bilinear grid sampling, and then we convert that to discrete sampling, fine-tune for a little bit, and then the final model only uses discrete sampling. So now let's go to the actual source code. So this is the repository for RTDETR. My previous videos were about this RTDETR v1 PyTorch, and now we'll go to RTDETR v2 PyTorch. I will leave the link to the instructions how to install everything in the description, as well as the actual Jupyter notebook that I will be showing right now. So this is the Jupyter notebook with all the usual stuff on how to actually plot images to see what the model is being trained on. This is the way to sniff out the arguments to be able to launch everything in the same way as in this training script. And then similar to RTDETR v1, all the actual logic is hidden inside this solver class. And so this is how we can sort of initialize it to actually load the dataset and everything. And this is how our favorite first image in the Coco dataset looks like. And again, just by repeatedly executing the cell, we can get a sense of what sort of data augmentations are used. So you can see that once again, the image is resized to the same size all the time, although sometimes it will basically get downscaled to a smaller image and then padded with this black area. Over here, for example, we can see that something weird now happens to the color quite often. So it's the actual augmentation is now much more extensive than in v1 version. So here, for example, we can see that the broccoli turned blue for some reason. So we can take a look at what these augmentations are called. So this blueness is called random photometric distort, which basically adjusts brightness and all the colors randomly every time you call it, which allow the model to basically get adjusted to different color distributions. And everything else is pretty much similar to v1. So we have random zoom out, RU crop, horizontal flip, and then everything is resized into 640 by 640 dimensions. So in the paper, they have this thing called dynamic data augmentation. So as we'll see a bit later, this basically is saying that we start training with all of these augmentations, and then after some epochs towards the end, we disable some of them, right? Like random photometric distort. And in the actual paper, they say that the ones getting disabled are random photometric distort, random zoom out, random RU crop, and multi-scale input. Then apart from dataset, we also have a data loader. So dataset fetches just one image from Coco dataset in this case, and then data loader actually unites several images into batch. And again, this is part of a solver, and this is how we can just iterate over it and just fetch one batch from the data loader. And so one element like this will contain, so batch size is 16, so one element will contain 16 images and the actual targets for these images. So this the shape of that. So again, all of the images are resized into the same shape before being passed to the actual model. And because of that, we don't need any special code for collation in the data loader. We can just take 16 independent images and just unite them all into one tensor. Batch size is 16. We get three colors per image. This is how the actual image looks like from the data loader. So augmentations are all from the data set, so they're the same as we've seen before. And this is how we can call the actual model. So solver.model gives us the model. We have targets and images that we've got from the batch. And here's how we can apply the model. We can plot the results. So primary output of the model will have 300 queries. So that's spread logit shape. So we get one probability prediction for each of the classes in the Coco dataset, plus one special no object class for background prediction. For predicted bounded boxes, we get 4 numbers per bounding box, so x and y coordinates of center and one of the corners. We also have what is called denoising outputs, because they participate in the loss. So again, RTDETR v2 follows v1 and basically inherits the logic from Dino and DNDETR, wherein we have 300 of normal queries that participate in Hungarian matching loss and all of that. On top of that, we generate special denoising queries that skip matching and get connected directly to ground truth objects, and that helps train the model. So they are being passed out as these denoising queries and denoising outputs. Now let's read the actual code of the model. So let's print out what that is. So the model is called RTDETR, and so I can just search for it in the code, and I can see it over here. So it inherits from pytorch.nn.module, which means that we probably need to break in the beginning of the forward method, and then I can just say that I want to debug into this cell, into Python notebook, and voila, here I am. So let me print the shape of the input first. So this is again 16 images, 640 by 640. So backbone and encoder will not read today. They're the same as in V1, but let's just quickly step through them and see how the shape of X changes. So we've started with just single tensor 640 by 640. After being passed through the backbone, we get these 4 downsampled versions of the image. So they all have byte dimension of 16. And then the first image has embedding dimension of 128 and then 80 by 80 pixels. Second picture feature map is slightly bigger in embedding dimensions, slightly smaller in actual pixel resolution. And then the final image is 512 in embedding dimension and then 20 by 20 pixel resolution. And that is getting passed into the encoder. After that, we can see that we still get these 3 images of different scales, so 80 by 80, 40 by 40, 20 by 20. Embedding dimension is now 256 for all of them. So before passing through transformer, we basically resized them, passing through single convolution. So this encoder is the one I was talking about in the previous video. So this is the special hybrid encoder that basically applies full pairwise self-attention only to the smallest image, 20 by 20, and then special scheme of upsampling and downsampling the different resolution images to propagate the same signal. So this is called the hybrid encoder. And then we call the actual decoder. So let's print the type of that. That's now RTDETR transform v2. Again, looking for that in the code. Here it is. So I can break at the very beginning of the forward method. Next, some transformations will be done. So we get these features as a list of length 3, right? So 3 different scales of features. Before passing that through the decoder, we're going to flatten everything out, and that happens in this get encoder input function. So let me just continue through here, print out the output. Memory.shape is now single tensor with 16 by 8400 by 256. So this 8400, that's basically the flattened version of all 3 images concatenated together. You can check that by just multiplying 80 by 80 plus 40 by 40 plus 20 by 20, and that's exactly what you get. So we basically flatten each image, which means that we take it column by column and just basically flatten out, putting every pixel in a sequence, and we put all 3 images in the same sequence, and this is what we pass as memory as encoder output. Then we set up two sets of queries. So the denoising set of queries that basically has ground truth objects with added noise to make the actual task more complex for the model. And that's one set. And then second set is the actual queries that get selected from encoder output. Again, the selection process is originating in Dino, and I've talked extensively about that in my previous video about RTDETR v1. So let me continue through all of that and just print everything that gets passed into the decoder. So we now have these 480 queries in total, so 300 normal queries, 180 denoising queries. The queries themselves have 256 dimension embedding, and then we have our memory. And for memory, the sequence length is 8K, and the embedding dimension is the same. So then we want to read the actual decoder. Type of the decoder is transformer decoder. It's all defined in the same file, so you can just find it quickly like that. So before we read this, let me actually go back to slides and explain deformable attention once again. So looking at this diagram from Deformable Attention, here is what we need to perform the actual deformable attention. So this is the encoder output. So 3 feature scales all flattened, concatenated together, and this is being passed as the side input to the decoder. We have our object queries that we've got selected actually from the same encoder output, but that doesn't matter, so we have them now. So we have the queries. So to perform the actual deformable attention, we need reference points, which are like the points of attention, the centers of attention. And then from these centers of attention, we basically predict 3 offsets as depicted here, or variable number of offsets, to say that, okay, well, take 3 pixels up and 3 to the left to get sampling offset number 1, 2 to the right to get sampling point number 2, and so on. So we get reference points as center, we get sampling offsets as the actual delta that we need to add to the reference point to get the actual point we need to sample. And then we have the actual attention weights. And as we'll see shortly, the attention weights are also just computed using linear projection from the query itself. So this is the code of the decoder. So main thing the decoder does is it iterates over all the layers. There's going to be like 6 of them probably. And then it does this thing called reference points update. So what that means is we have the reference points, and reference points basically represent the center of attention, which makes sense to do it in the actual center of the bounding box that we are about to detect. And so layer by layer, the model improves its understanding of object detection. It improves the current estimate of where the actual object is. And so we, upon improving of that understanding, we update the current bounding box and we update the reference point to point our attention in the new direction. And so this is what is happening in this code here surrounding the actual layer call. So let me break at the very beginning of this layer call and actually print what the type of the layer is. So the layer is transformer decoder layer. Let's see how many we have. So we have just 3 layers. So this is the smaller version of RTDETR that is even faster, but not as accurate as some of the bigger versions. So now let's break at the very beginning of the decoder layer. So here's the decoder layer. Again, we need the forward method. We continue to here. And let's once again just print all the shapes to make sure we know what they are. So we have target, which is basically the queries, in case we talk about input, but then on the next iteration, the same output will be passed as queries, query input for the next layer. That's why it's called targets. So then we have these reference points. So reference points, again, for every of the 480 queries, we get 4 coordinates of basically expected size and center of the bounding box. We have memory. That is the thingy that we've got flattened from the encoder output. So here we can see that query, which is identical to key in this case, we get it from the query inputs called here the target. So this with both embed function, that's basically just adding positional embedding if it's actually present, which it is. Then we call self-attention. So again, we are talking about decoder now, which means that we have queries as one input, we have memory as another input. We will have several steps. So in the first step, we have self-attention, where we let queries attend to each other and exchange information between each other. And then we also have cross-attention, where we now let queries look at the image and also exchange information with the image. So self-attention is rather simple. It is defined as just vanilla PyTorch multi-head attention. So it's just an official PyTorch layer with documentation. We can see that here we use queries and keys and values from the same source, basically. So we use these 408 queries as all 3 of these, and that's where we get this output of the self-attention. So this plus here is residual connection. Then we have norm for normalization. Then we have cross-attention. So for cross-attention, we will have the actual query inputs, and we have memory inputs. So you can see that the actual function ends shortly after that. Again, after one iteration of residual normalization, and then another iteration of feed-forward network and another residual. So the most interesting part happens here in the cross-attention. So cross-attention is called a mass deformable attention function. So go to definition, let's see what it looks like. Again, this one inherits from an end.module. So we need the forward method and just break here. So then what we do, we have the value and we pass that through the value projection. So value projection, this is just a linear layer that takes in 256 dimension and outputs 256. So the way it will be applied, so this is partly why we sort of reshuffled our shapes a little bit. So this linear transformation will always be applied to the last dimension, which means that it will take each of the 16 images, each of these 8K pixels, and then apply linear layer to this final embedding that we've seen as a final dimension. And it will perform that independently for each of these. So it will not propagate signal through the pixels from one pixel to another. It will just apply one linear layer within that pixel, unlike convolution, for example. So then we don't have any masks, so value mask is none. Then we have the logic about the actual sampling offsets and sampling weight and attention weights. So sampling offsets, again, is just a linear layer, but this time it outputs 48. So what is that? Okay, let's try to guess it. So first of all, each sampling offsets for one query, that's basically 2 numbers, X and Y offset, right? In addition, we have these 2 thingies called number of heads and number of points, right? So this number of points list is actually a major thing for RTDETR v2, and it shows how many points we'll actually use for attention on each of the 3 levels. And we can see here that we just take 1 point per level in this small version of the model. We can search in the code to find different model configs and just see what different variants are there. And we can see that there are some models with 111, 222, 333, 444, and this is pretty much it. So despite the fact that it's actually supported in the code, we will not have different numbers of points per different level. Instead, we just have different variants of the model with different numbers of points. That was not really clear from the paper, so I'm glad I've actually looked in the code. And so in this particular model, we have 3 points in total, 1 per each level. And in addition, we have the multi-headed attention. And number of heads is 8, which means basically that we're going to repeat the same attention operation 8 times independently. So we'll compute attention masks, attention weights 8 times, we'll compute sampling offsets 8 times, and then perform, and then basically unite the result. So this is called multi-headed attention. This is the classic for all the transformers nowadays. And so 8 heads times 3 points for all the levels times 2 coordinates per point, that gives us exactly 48, which we've seen here in this sampling offsets linear layer. So this is what it does. And we can see in the code that we basically project everything down to 48 first, and then reshape it in such a way to actually make it more obvious what is going on. So we get 16 images, 480 queries, 8 heads, and then 3 points and 2 coordinates per point. Then we have attention weights. So attention weights are quite similar, but now we only have 1 weight per point. So instead of 48, we'll have 24. And again, we reshape it in such a way that we basically have 16 by 8, 480, 8 heads, and then 3 points, and then just 1 number per point. So then we have the actual code to get sampling locations, the actual pixels we will look at from offsets and reference points. And so we can see here that there are 2 options here. Either we get just 2 coordinates per reference points, so x and y, or we get 4 of them, and that's x and y coordinates of the reference points, as well as the size, so height and width of expected attention that we want. And you can see that in our case, we actually get 4. And so what will happen is, well, we first basically multiply the offsets that we've predicted by the height and width that we get from the second 2 coordinates of these reference points. So now these 2 coordinates basically modify how spread out our attention will be. And then we add that to the first 2 coordinates. So that basically controls where will the center of attention be. And out of that we get actual sampling locations. So sampling locations is now this giant tender of 8 by 3 by 2. So 8 heads, for each head we have 3 points, and we have 2 coordinates per each point. And let's just print how that looks like for first image, first query, first head, right? And that's what we see. So unfortunately this is the brand new initialized model, so we don't really see much difference in these numbers yet. They will become different once we actually train the model. But interesting detail here is that this is a floating point number, and this actually looks like a floating point number from 0 to 1. So we haven't applied the actual height and width dimension of the image that we know. So for now, all of these basically refer to some arbitrary location that might not actually land exactly in the pixel, might land somewhere in between. Then we have this deformable attention function. So let me continue to this one. So it's core func v2, and just break here, continue. So now we do another permutation. Let me just continue a bit forward and print the result of this. So we have this value list with the following shapes. So what we did right now, we basically had one flattened sequence of encoder outputs with pixels from 3 images all concatenated together. We also got in these spatial shapes, which basically encode like what were the original dimensions of 3 images. And then we basically split them back into 3 independent sequences, because this is how we'll need to compute our variable number of sampling points per level. Then we do some permutations and more flattening. So what this thing does is it now moves the head dimension into the batch dimension, basically saying that, computing the same thing for 8 heads is the same as computing it for 8 different images, because they should not depend on each other. And from there we get this sampling grids object, where now batch dimension got multiplied by the head dimension. We still have 480 queries and now 3 points per query, 2 coordinates. And we split that into 3 independent arrays, right? Because non-point list is this array of length 3. And then we iterate over these levels, compute the actual sampling of the locations for each level independently. And we can see this second important thingy in the entire RTDETR v2 is this sampling method. So it has 2 options: method default, method discrete. So for default method, we use this f.gridSample operation. Let me just continue to here and just print what the shapes are. So we have the value. The value is like the input that we get, and we don't really care, about the type of this, right? So it says that, it's this 80 by 80, so I've basically unflattened my highest resolution level, and I have some values for the pixels, right? And I have my sampling grid, which are sampling locations, right? And this is how they look like. So they are floating point numbers. And so applying this pytorch.f.gridSample operation basically performs this process of indexing into a vector. So this can be briefly explained as this. So imagine that we have a tensor like this, right? So normally to index into a vector, you use integer index. So you can say something like x with index 1, and that gives you the element with offset 1. Right, and that is equal to 2 in this case. So bilinear grid sampling is basically saying that I want, so this is one-dimensional case, right? But basically I want x with index 1.5 or 1.33. And this will perform, in one-dimensional case, linear interpolation. So in the case of 1.37, that will see that it's actually closer to this 2 here than to the 3 here, and so it will be the result of the sampling will be something like 2.35 or something like that. And this PyTorch f.gridSample does the same, but for 2-dimensional case. And so the output of that is, let me just compute the shape, is of the shape 128, so that's batch dimension times head dimension, times 32, that's the shortened embedding dimension, because we had 256, but we divided that into 8 equal parts for 8 different heads, times query dimension times 1. So this is the output of this sampling. So we've basically computed the output of this entire level. And then we basically concatenate that to the output and return that. So this was the default sampling method. And then the second option here, discrete sampling method, instead of using this f.gridSample, it is going to just convert this tensor of sampling coordinates to int64. So this is an integer. Upon doing so, we basically get rid of the fractional part of the sampling. And then we just use that sampling chord thingy in here in square brackets, which means that we basically index into a tensor using this normal square bracket syntax. So what this does is it now gets rid of the fractional part, which means that we basically lose some information. It's also not differentiable. So from this point forward, we cannot pass gradient of the output with respect to this sampling location. So we still can compute that gradient with respect to input value, but not the sampling location, not the location of the attention itself. And this is what we return. So this basically concludes the deformable attention layer. So we can see like what is the logic of training of this if we search for the config of the model that we need. So let's say that we want to look at this ResNet 18 based variants. So I have this variant, which is basically a ResNet 18 based trained on COCO dataset. And then this DSP version is also ResNet 18 based, but now with discrete sampling. And if we look here, it's basically starts with this model, this tuning model here, RTDETR R18VD 120E COCO. So basically, the logic here is the following. So first we start with this model, right? So we can actually look into the config for this one, right? So this is the normal model that does not use discrete sample, and we train it for 120 epochs. Then we save that as weights. We initialize our new model with these weights. Now we use discrete sampling, and we train for only 36 epochs. And that is to basically let the model adjust to this discrete sampling. So once again, what just happened in this core function for deformable attention? So we got our sampling points, we got out the actual outputs. So this entire function can be viewed as just indexing operation, which does that either using bilinear interpolation and this grid sample, or discrete sampling, which just converts the indices to integer. We've also sort of skipped through that, but here is the point that uses the actual num points list, and that is the list of the number of attention points we want per every level. And in here, all of them are equal, but in theory, we can put something like 3 to 1 in here and actually have different number of sampling points per different scale. So for example, have 3 sampling points for 80 by 80 high resolution image, and then just 1 sampling point for 20 by 20. And the way this is written in the paper, it sort of looks like that's what they did, but not really. They always use the same amount of points. Another thing that we need to look at is this thingy described in the paper as dynamic data augmentation and scale adaptive hyperparameters customization. So let's start with the first one. So if we look at some of the configs of the model, we'll see the thing called stop epoch. And this thing basically says that we are going to disable some of the augmentations towards the end of the training. So this specific config has 120 epochs in total, and on epoch number 117, it's going to disable some of the data loading transformation that we've seen. Which specific transformation is described in this data loader config. So it says that after reaching stop epoch, we're going to disable this random photometric distort, which makes pictures look bluish or some other weird color. We're going to disable this random zoom out and random IU crop. We can look for the code here. So this is implemented in this compose transform that we've seen. If we look at the original Python notebook, the dataset says that it's going to apply the composition of these transformations. So the upper method is compose, and here are all the transformations that are being composed. And so in the code for this compose transformation, we have 2 functions, so step epoch forward and just forward. So after we've reached the stop epoch forward, we basically check if this specific transform is sort of written in this config. And if it is, and we have reached the stop epoch, we just skip it. If not, we actually apply this transformation. And so what it does is, after epoch number 117, we start skipping these transformations. So that's one thing. Another thing that is happening here, so in the paper that's described as stopping this multi-scale input, and here it is implemented using this collate function. So collate function is the function that is uniting several images into a batch. And here it actually applies this multi-scale transformation. And so what is happening here is we have scales, and we can look at what scales there are over here. And if we do have scales and we haven't yet reached this stop epoch, we're going to randomly resize the entire batch of images, right? So sometimes we might have images of 640, sometimes we might have images of, say, 480, and so on. So this is done to basically adapt the model to different scales. So for example, you will have one pre-trained model that is able to work with different resolutions, and then you can plug it into various scenarios depending on what sort of camera you use in your actual project and so on. And so this logic is done in the collate function because we want to resize the entire batch. We don't want to resize every image individually and then pad them and so on. So we want all of them to have equal sizes after resizing. And we also have this stop epoch logic. So we stop doing that towards the end of the training. So this is about it regarding everything that happened in V2. So overall, the model is roughly the same, although today we've dug slightly deeper than the last time into the actual deformable attention. We can also see the results. So you can see here that, that's a slight improvement, but mostly for the lighter versions of the model. So for example, ResNet 101 based model, which is the biggest, which has 64 RPS, basically didn't change that much. But then the smallest model based on ResNet 18, which yields up to 200 requests per second, this got the biggest improvement. So I would say this affects lighter versions of the model more. Nevertheless, still nice. Still, as they say, bag of freebies. So this is it for today. Thanks everyone for listening. I hope that was useful, and see you next time.